Okay, hi. Today we're doing something a little bit special. It's going to be chemistry. And okay, according to my chemistry textbook, we are currently on group 1, learning about group 1 elements. So just show you really quick. This is 4.4 about group 1 elements, and we're going to be just doing notes about this chapter. So let's try and finish this as soon as possible. So far, I've written down the elements in group 1 so far, and this is how I'm memorizing them. Lina nak kawin, rubidium case first. Makes no sense. Lina, this is in Bahasa Melayu, wants to marry you, but you must give her a rubidium case first. Cool? Okay, amazing. Now over here, they're giving us this table, and I think I'm gonna write down this, which is what they can be used for. So just give me a moment, and we're gonna copy this down. Uppercase, okay. Okay, never mind. You just look at me writing it. So over at lithium, it is used in used in battery production. Hold up, let me get my notes. Okay, you can add some extra facts. Why is it used in battery production? Hold on, let me get a different pen. Because lithium batteries, Li batteries, BAT, are powerful and lightweight. Okay. The sodium handling. Sodium can be used in sodium vapor. Used in and I'm gonna write here, it also has a table salt use in sodium chloride foam. Okay, potassium can be used in fertilizers. That should be it. Then okay, that's all, but I have some notes that give extras. So example refers caesium with rubidium. Is that anything for rubidium? Used in manufacture of photocells. It's a small light sensor. Okay, and then we have caesium, which is used in atomic clocks. Which is an extremely accurate type of clock that is regulated by vibrations of an atomic or molecular system such as caesium. I'm not writing that, that's way too long. So caesium can also be used in photoelectric cells. Do I have a spot to write that? Used in photoelectric cells. Okay, then we have francium, which does not have anything too special. Perhaps it's too reactive for anything. So there's also some bonuses I can put for sodium, which is you can write, it can be baking soda as well. So baking soda, and then the formula for baking soda is NaHCO3. There you go. Okay, so we're done with this part of the textbook. So we're gonna go through this at the end of the lesson. We should be able to generalize the changes of physical properties of the elements we're going to investigate through experiments. Okay, cool. We have to talk about the next thing, which is arguably a lot more important, which is the change of physical properties. So I'm gonna write this at the bottom here. Physical properties of elements. And this is, you can't really see it. And this is going down group 1. Okay. First and foremost, we can draw the electronic table. So you can put over here alkaline metal. Okay, and then the electron arrangement. I think I'm only gonna go up to potassium because they usually don't ask you past potassium. So sodium, Na, potassium. Okay, let's draw a line. It's quite slanted. Not sure what I can do about that. Deary me. Okay. So lithium is 2.1. This is 2.8.1, and this is 2.8.8.1. Okay, I finished my notes, and I think I'm going to give like a quick run through on group 1 of all the elements. So first, we talk about the elements in group 1 in the first place. How do I memorize it? Lina nak kawin rubidium case first. Lina wants to marry, gotta give her a rubidium case first. That is lithium, sodium, Na, natrium. Kawin is potassium, rubidium is rubidium, and CS is caesium, Fr is francium. Okay, in my opinion, these three are definitely more important because they are much more useful compared to the other 3. Now we'll go about them in a minute. So first, let's talk about this. What are their uses? So lithium can be used in battery production because lithium batteries are powerful and lightweight. Moving onwards to sodium, which can be used in sodium vapor lamps, which grow pretty bright. They grow like a bright yellow color. They can also be used as table salt in this form of sodium chloride, and they can also be baking soda with the formula of NaHCO3, so not just by itself, with other elements. Now for potassium, it can be used in fertilizers, and for the others, this is more like extra information. Rubidium can be used in the manufacturing of photocells, which is like a small light sensor. Meanwhile, caesium can be used in atomic clocks, which are these clocks that are very, very accurate because they go by vibrations and whatnot. Now, francium has no usage, and going back to caesium can be used in photoelectric cells. Going back to francium doesn't have a known use, at least in the textbook, and it can be explained because we're going to go on just the physical and chemical properties first. Going down that rubidium, caesium, and francium, they're kind of special. They have shiny surfaces, a low melting point, and low boiling point, which is the same as lithium and sodium and potassium. Now, special things about them, the rubidium and caesium usually are combined with other elements. This means they are difficult to be isolated chemically. Now, for francium, is an unstable radioactive isotope with a short half-life. Thus, because of how unstable and how short of a half-life it has, it is not very useful. There's not many known uses for it because it doesn't seem to be very useful, convenient to be used. Moreover, that rubidium, caesium, and francium, if you go down, going down the group 1, elements in group 1, they become more and more reactive. Thus, rubidium, caesium, and francium are extremely reactive to water and oxygen. Now, going back, let's look a little bit at the electron arrangements. So lithium is 2.1, sodium is 2.8.1, potassium is 2.8.8.1. So if we were to write down the number of electrons, this would be 3, this would be 11, and this would be 10 plus 18 plus 1, 19. Then coming over here, we have to talk a little bit about their atomic radius. Here are the values, the melting point and boiling point. All you have to know is that through decreasing, as you go down, they become the melting point and boiling point decrease, while the atomic radius goes the opposite way. It increases as you go down, and it is explained here. The melting and boiling point decrease as the atomic size will increase, because the force of attraction between atoms is weaker. The less heat energy is required to overcome the weaker forms of attraction between atoms. Because they have become a lot larger, this causes the heat energy needed to overcome their bonds to be a lot less, a lot weaker. I know. And moving on, we have the physical properties. For example, they are soft metals. So soft metals, they are soft metals with gray shiny surface. They are also known as alkaline metals. Now, coming over here, the density of these metals is low, and they float on the surface of water. There's an experiment all for this. Now, the melting and boiling point is high, but compared to other metals, it is low. So honestly, this part not that needed. You could honestly just write that their melting and boiling point is low compared to other metals. Now, coming over here, we have to know that the atomic radius, when it increases, is referring to the number of shells occupied that has electrons. So this is what this is talking about. Okay. Now, finally, let's talk about the chemical properties. First, to know this formula, M is equivalent to M positive plus E negative. E is the electron. M, it just has a positive charge. Why? M refers to matter, by the way, not mass, not momentum, not anything. Okay? It's because when an atom is here, and when you donate one electron, remember, you cannot donate your protons or your nucleons. It's only not your nucleons, your neutrons. It's only your electrons that can go in and out. So when the negative charge leaves the atom, you are left with less electrons and more protons. So example, if you had 12 protons and 12 electrons, you now have 11 electrons, making it so that you are now a positively charged. You're not positively charged. So if you want to look at the equations, you can, I've written them all over here. We can have a brief look at them, which is write the chemical equation for the reaction of lithium. So, okay, 2 lithium, which is, all of these are metals are solid, and then water is a liquid. Coming together, you get 2 lithium OH, which is an aqueous solution with H2. Because the O has been subbed in here, while the H2 has been placed to become hydrogen gas. Same thing here. For 4 lithium, they're all solids. Oxygen gas is all gas form, and they all still become a solid. As the oxygen is burned, oxygen the two of them produce oxide, lithium oxide, sodium oxide, and potassium oxide. And we know that they do not need to go through, example, there is a more complicated way, this one. They do not have to use this method to find the oxide version of them because they are very reactive metals. Coming back to here, we have lithium, sodium, and potassium. Combining with chlorine gas, you will get lithium chloride, sodium chloride, and potassium chloride. Again, they can immediately react because they are extremely reactive. Okay, let me put this over. Okay, finally, we're here to talk about the reactivity. So, the reactivity of alkali or alkaline metals is due to the tendency of an atom to donate its valence electrons. In here, there's only one valence electron, thus being placed in group 1, because group 1 is according to what is your valence electron, while your period is determined by how many shells you have. Okay, so the number of shells with electrons, which remember determines your atomic radius, when going down group 1, okay, it will increase. So thus it will increase the atomic size. So the position of the valence electron is placed further away from the nucleus of an atom. You understand? Because if an atom was here, and as the atomic radius becomes bigger, the valence electron, which is on the outside, will be the distance between the nucleus will become bigger and bigger as you grow more and more shells. Thus, the nuclear attraction force towards the valence electron becomes weaker. The attraction force to pull it back in here becomes a lot weaker. Thus, this valence electron is much easier to be donated, thus making it more reactive. And that is all that is regarding about this subtopic, chapter 4.4. Thank you so much for watching. I'm going to go to bed now. Bye bye.